Do you believe that our Sun once had a family 4.6 billion years ago, in the heart of a cold and silent cloud of dust within the Milky Way? Thousands of stars were born together, among them the Sun. Those stars once shone beside each other, sharing the same breath. Then over time that cluster dissolved, and each child of light was slowly carried away by the spiral currents of the galaxy, lost among the endless sea of stars. Now astronomers are tracing the faint remnants of those memories in the light of the stars, in the chemical composition of meteorites, in the numbers the universe has quietly preserved for billions of years. They are searching for the Sun's lost sister stars that may still be burning somewhere in the sky. Because finding the Sun's long-lost family is not only a scientific journey, but also a journey back to our own origins, to the place where lifelight and the memory of the cosmos merge into one. Now let's begin the journey back to the first moment when light was born, and listen to the story of the family the Sun left behind. A community of suns, each cradled by the same primordial mist, before being scattered across the Milky Way like seeds carried by a galactic wind. Not every star survives that dispersal with a sense of belonging. Some are ejected, violently thrown into the quiet void by gravitational clashes. Others simply wander, pulled gently by the tides of the galaxy. Perhaps our Sun was one of them, a wanderer who forgot where it came from. Or perhaps it remembers somewhere in its burning heart the resonance of the cluster that first embraced it. Astronomers rarely deal in romance, but data often hides poetry. When we map the motions of young stars, we see patterns, streams, and families still faintly bound by origin. In those flows, in those echoes of movement, we glimpse the story of how stars are born not alone, but together, breathing in sync before time scatters them into anonymity. Inside every molecular cloud, the rules are strict, even merciless. Gravity pulls inward, pressure pushes outward. Temperature decides the winner. The colder the gas, the slower the atoms move, and the easier gravity can weave its net. Only when the temperature falls to about 10 degrees above absolute zero does collapse become inevitable. Then dense knots form, each one the embryo of a future sun. It's a quiet chaos, pockets of hydrogen collapsing, spinning, heating 1,000 miniature worlds being born in parallel. Radiation begins to pulse through the darkness, carving patterns of gold and violet through the gas. What looks serene in photographs is in truth a violent symphony of forces, and among those countless beginnings was ours. The Sun was not alone when it opened its eyes to the universe. Around it, many others ignited blue giants that would burn fast and die young red dwarfs that would outlive the galaxies themselves, and stars much like our own, gentle and stable. Together they formed a temporary constellation that no longer exists. We call it the solar sibling cluster, though its shape, its boundaries, its story have long been erased by time. Yet the evidence remains. Traces of radioactive isotopes inside meteorites tell us that a nearby supernova once exploded close enough to touch the newborn solar system. Aluminum-26 and iron-60, short-lived isotopes that could only have been forged in the heart of a dying giant, found their way into the rocks that would become planets. They tell us the Sun was born not in isolation, but in a crowded, dangerous nursery, where the death of one star could ignite the birth of another. That idea that death and creation intertwined at the origin of our world is both terrifying and beautiful. It means our existence began in the echo of destruction, and somewhere out there among the billion stars that share our galaxy may still shine the remnants of that ancient family, the lost sisters of the Sun. But how many could there be if the original cluster contained several thousand members, 5,000, 10,000, maybe 20? Then statistically many of them still exist. The smaller ones, the red dwarfs, could still be burning faintly today, patient and enduring. The massive ones, the blue suns, would have already perished, gone supernova long before life arose on Earth. Still somewhere, a few of those siblings may remain within a few hundred light years of us, their light blending silently into the background sky, indistinguishable from strangers. We look at the stars each night, never realizing that one of them might share the same birthplace as the Sun itself. If that's true, if even one of those stars still carries the same chemical signature, the same pulse of isotopes, then it would be a window into our origin story. Not metaphorical, but literal. A link to the moment when everything familiar, every ocean, every breath, every heartbeat, was still dust swirling in the same ancient mist. Science demands proof, not faith. But in the search for the Sun's lost sisters, both are required. proof to identify them through spectrum trajectory and time, faith to believe that memory can survive across billions of years of motion. Because the truth is, stars forget. Their paths twist under the influence of gravity warped by spiral arms and interstellar clouds. The family disperses, the traces fade, and eventually no one remembers who was born where. But sometimes in a moment of quiet observation the data whispers. It shows two stars moving in parallel across the galaxy, sharing not just direction but ancestry. And for an instant the universe seems to remember. The question remains, how do we find them? Where do we even begin to look in this ocean of light? The answer lies not in mythology, but in the language of physics. In the way we decode light itself in the orbits, we can trace backward through time. To find the sisters of the sun, we must become cartographers of the past, mapping not geography but memory. It's a journey that begins with the smallest clues, isotopes in a stone, the chemical lines in a spectrum, and stretches outward into the geometry of the Milky Way. And perhaps as we search through that map of forgotten stars, we might not only find where the sun came from, but rediscover what it means to have a home in a universe that forgets. If we wish to glimpse the childhood of our sun, we must look not at the sky, but at what has fallen from it. In meteorites, cold, ancient travellers that once drifted through the newborn solar system, we find the oldest memories of all. Each fragment is a message, a time capsule sealed before planets even existed. Inside these tiny stones, scientists have found the fingerprints of radioactive elements that no longer exist. Aluminum-26, iron-60, short-lived isotopes with half-lives so brief, just a few 100,000 years, that by now every trace of the original atoms has vanished. What remains are their descendants, the stable elements into which they decayed. By studying those remnants we can reconstruct when they were formed. And by what? Aluminum-26 can only be created in the explosive heart of a massive star, a supernova. Iron-60 too is born in that same furnace of death, and yet these isotopes were already mixed into the matter that became the planets almost immediately after they were forged. That means one thing, a supernova must have gone off near the cradle of our solar system, showering it with new elements, igniting the collapse of the surrounding gas, and triggering the birth of the sun itself. It's an astonishing conclusion, one that ties the beginning of everything we know to the end of something else. A dying giant may have sacrificed itself to give life to our world. In the echo of its explosion, the gas of the molecular cloud shuddered, fragmented, and fell inward, forming dozens, perhaps hundreds of young stars. Among them was the one we now call the Sun. The evidence fits the pattern. The radioactive traces in meteorites act as timestamps. They tell us how quickly the material cooled, how long it took for dust to condense into rock, and how close that supernova must have been. Not too close, or its blast would have destroyed everything. Not too far, or its isotopes would never have reached us in such abundance. Somewhere in that narrow window, in that precise balance of violence and distance, our solar system was born. It's difficult not to feel awe at that balance. Imagine a colossal explosion bright enough to outshine an entire galaxy, for weeks creating the very ingredients that would someday become oceans, air, and life. From chaos came chemistry, from fire equilibrium. The same shockwave that tore a star apart might have also gathered the dust that became the Earth. But isotopes are not the only clues. We can also read the orbits of distant objects, the scattered population beyond Neptune. Their elongated, tilted paths hint that long ago the young solar system was disturbed, nudged by gravitational encounters. Perhaps neighbouring stars, other newborns from the same cluster, passed close enough to tug at our outer disk, twisting the orbits of what would become comets. Those encounters, subtle but cumulative, left fingerprints written across billions of miles. Even now, the farthest regions of our system, the realm of Sedna and the Oort cloud, carry the faint memory of that crowded nursery. Every eccentric orbit, every odd tilt might be a trace of a long-lost sibling star that brushed by before drifting away forever. When astronomers piece these fragments together, the isotopes in meteorites, the orbits of distant bodies, the chemical patterns of the sun itself, a picture begins to emerge. It's not perfect. It's a mosaic full of gaps built from evidence older than any fossil, older than any mountain, older even than the Earth. But the story it tells is consistent. The sun was not born in isolation. It was one among thousands emerging in the aftermath of a cosmic detonation, and that realization gives weight to the question that guides this entire journey. If all those other stars were born beside us, where are they now? What became of the brothers and sisters that shared the same beginning? The answer may be written in the stars themselves, in their chemistry, in their motion, in the subtle harmony that only family carries. To uncover it, we must learn to read those stellar signatures as carefully as we read the meteorites. Because somewhere among the countless lights of the Milky Way, one may still hold the same spectral DNA as the Sun, the same pattern, the same trace of that ancient supernova, a sister shining quietly waiting to be recognized. Once long before the continents formed, and before the first ocean rippled under sunlight, our Sun belonged to a gathering, a luminous swarm moving together through the galaxy. That ancient cluster was its first home, a place where stars were born side by side, sharing heat, light and gravity. But like all families in the cosmos, it could not last forever. The same forces that brought those stars together would also tear them apart. At first, the cluster would have been dense and bright, like a floating jewel box suspended in the Milky Way. Thousands of young suns glittered in a shared cloud of gas, their winds sculpting the space around them, carving corridors through the dust. The scene must have been breathtaking, glowing nebulae streams of light and turbulence everywhere. Planets were just beginning to form their orbits, fragile, their futures uncertain. In such a place, every close encounter between neighbouring stars could shift destinies, nudging one planet toward stability and another toward destruction. Astronomers believe the Sun's birth cluster contained anywhere between 5 and 20,000 stars. Not enough to form a massive globular cluster, but far denser than the calm neighbourhood where we live now. We call this type of formation an open cluster, loosely bound, delicate, temporary. It is how most stars are born, and just as most families eventually drift apart, so too do these stellar kin. As young stars ignite, their combined radiation pushes away the gas that once held them together. Without that soft, invisible glue of matter, gravity weakens. Slowly, imperceptibly, the cluster begins to breathe outward. Each star drifts a little farther from its siblings. Some are hurled out, violently accelerated by the complex dance of mutual attraction. Others simply glide away, following the curved currents of galactic motion. Over time, what began as a tightly packed cradle becomes a diffuse memory, a trail of stars stretched thin across thousands of light years. That process is called dispersal, and once it begins, it never truly stops. Simulations show that a cluster like the Sun's could dissolve completely in just a few 100 million years, a brief moment on cosmic timescales. If the Sun was born 4.6 billion years ago, its siblings have had more than enough time to scatter throughout the galaxy. Some may now reside near the galactic centre, others at the rim, and some perhaps only a few hundred light years from us, invisible among billions of strangers. This dispersal wasn't random. The Milky Way itself, its tides, its spiral arms, its waves of density shape the paths of these stars. Just as the ocean shapes the movement of drifting boats, the gravitational currents of the galaxy slowly carried each sibling along a different route. The Sun too was swept along this tide, completing one galactic orbit every 200 million years. In that time, it has circled the galaxy more than 20 times enough for any trace of its birthplace to fade beyond recognition. And yet, if we could rewind the motions of every star in our region running the galaxy backward like an ancient clock, we might see them converge. Their trajectories, scattered and tangled, would slowly draw inward, spiralling toward the same patch of space where our Sun was born. That invisible intersection that lost point of origin is the ghost of the solar sibling cluster. Today it no longer exists as a single object. No telescope can find it. But its remnants are still out there, glowing quietly hidden among billions. Some of those stars have likely outlived their brighter sisters. Others have long since burned out, leaving only white dwarfs or clouds of remnants. The family, like all families, has changed beyond recognition. And yet something of that ancient unity remains in chemistry and motion, in the delicate symmetry that still binds those who shared the same birth. If we could trace that symmetry, if we could follow it through the noise of the galaxy, perhaps we could find them again. To search for them is not just to seek knowledge. It is to listen for an echo that began billions of years ago, an echo of shared light, shared dust, shared creation. It is to ask whether the Sun, radiant and alone in our sky, still remembers where it came from. Perhaps one day, through data and patience, we will see that forgotten pattern emerge again, a faint constellation connecting the scattered sisters of the Sun, shining together for the first time in billions of years. Even after billions of years, faint clues remain quiet evidence, whispering that the Sun's long-lost siblings might still exist somewhere in the Milky Way, not many, but perhaps a few thousand, and among them some may still be shining tonight, hidden in plain sight. When scientists simulate the early life of the solar system, they estimate that our Sun's birth cluster once held several thousand stars, maybe 5, maybe 20,000, a moderate-sized family compared to the massive globular clusters that host millions. Such open clusters are temporary by nature. Their gravity is weak, their hearts fragile, and once the supporting gas is blown away by stellar winds, the stars begin to drift apart. Yet most of those stars, if they were small and dim red dwarfs or K-type stars, would still be alive today. Unlike blue giants, which burn out in a few million years, these faint suns can last tens or even hundreds of billions of years. That means mathematically, many of the Sun's original companions still exist. The question is not whether they survive, but where they have gone. Time and motion are relentless sculptors. Over 4.5 billion years, the Sun and its siblings have circled the galaxy more than 20 times. Each orbit reshuffled them like grains of dust in a cosmic current, pulled by the Milky Way's spiral arms, its giant molecular clouds, and the tidal forces near the galactic core. Every encounter, every subtle nudge changed their trajectories ever so slightly until the memory of their shared path dissolved completely. If we could see the galaxy in slow motion, we would witness this dispersal like a ballet of fire. Thousands of stars drifting outward from a single glowing seed, expanding, scattering, fading into the grand river of starlight, each one carrying the same elemental signature, the same mixture of hydrogen, helium, and trace metals, a genetic imprint of the cloud that bore them. Astronomers sometimes call this the Sun's stellar DNA. Just as siblings on Earth share the same ancestry, stars born from the same molecular cloud share the same chemistry. Their blood, if one could call it that, contains the same ratio of heavy elements, sodium, magnesium, silicon, iron, in proportions unique to that one birthplace. To find a solar sibling then is to perform a kind of galactic genealogy, a search not for light but for lineage. And yet even chemical similarity is not enough. Stars can look alike by coincidence, born in different regions yet forged under similar conditions. To prove family, we need more than appearance. We need motion. Each star in the Milky Way drifts through space on its own orbit, guided by the invisible gravity of billions of others. If we could measure a star's precise velocity, its direction, and its distance, we could rewind its journey, tracing it backward through time to see where it once was. If two stars, after billions of years of divergence, trace back to the same point in space and time, that convergence becomes a clue. Perhaps then they were born together. This is no small task. Even with modern instruments, the uncertainties grow enormous when extrapolated over billions of years. A fraction of a kilometre per second in measurement error becomes a vast gulf of light years after enough time passes. And yet, with missions like Gaia, humanity now holds the tools to attempt this impossible map, to draw lines across the galaxy's memory, reconnecting the scattered fragments of the Sun's lost family. Somewhere among the soft haze of the night sky could be one of those stars, maybe faint, maybe unnoticed, perhaps no different from thousands of others. But in its spectrum lies the same silent melody, the same rhythm of elements that once pulsed through the Sun's own birth cloud. To see that star would be to look into a mirror billions of years old to glimpse the origin of everything we know. And even if we never find it, the search itself changes us. It reminds us that our Sun is not a solitary being drifting through eternity, but part of a greater story, a family scattered, not lost. Each sunrise, each reflection on the ocean's surface carries within it the light of a shared beginning. For in the language of the stars, nothing truly vanishes. It only drifts farther away, waiting for the moment when memory and curiosity find it again. To understand where the Sun truly came from, we must travel even further back, before the planets, before the light, to the cold, dense darkness that existed before the first ignition. Every star begins there in silence. In the vast structure of our galaxy, between the luminous arms that cradle stars and nebulae, lie regions of shadow, enormous molecular clouds composed mostly of hydrogen and helium, threaded with grains of cosmic dust. They stretch across light years, invisible to the human eye and colder than anything on Earth. 10 degrees above absolute zero, that is the threshold where gravity begins to win. The laws of physics are simple but absolute. When gas cools, its atoms move slower, the pressure weakens, and gravity begins to gather the drifting particles inward. Slowly the cloud thickens in places, forming invisible knots, the embryos of future suns. Each one spins as it collapses, conserving angular momentum, heating at the core. The temperature rises from 10 Kelvin to thousands, then to millions until fusion begins, and in that instant a star is born. This process, though serene in the telescope's distant gaze, is turbulent up close. Winds from nearby stars sweep through the gas-carving cavities and filaments. Shock waves from supernovae ripple through the cloud, compressing it in bursts. Gravity does not act alone, it needs a trigger. Sometimes that trigger is the death of a nearby star, sometimes the collision of two clouds, sometimes the gentle compression from the spiral density waves that move through the arms of the Milky Way like sound through air. Our Sun, too, was likely awakened by such a spark. The isotopic fingerprints we discovered earlier, aluminum-26 iron-60, suggest a nearby explosion, a supernova, whose dying breath shook the gas into collapse. In that moment, hundreds or even thousands of fragments began to condense around us, each one destined to ignite. The cloud that would become the Sun's cluster was no different. In that single region so small compared to the galaxy yet infinite in consequence, hundreds of young stars were kindled at once. The early cluster would have glowed like a nursery fire, chaotic, hot, alive. Imagine it newborn suns rising out of the same swirling mist, their light carving shadows on each other's faces. The space between them filled with radiation and charged particles sculpting the gas into arcs and waves. Massive blue stars blazed fiercely and died quickly, while smaller, gentler stars like our own settled into long, steady lives. It was a moment of collective creation, a generation of suns born from one breath of the cosmos. And yet, it was also fragile. The same energy that gave them life began to erode their home. The ultraviolet winds from the youngest giants stripped away the remaining gas. Without that binding material, the cluster's gravitational web weakened. Soon, each star began to drift on its own, pulled by subtle tides. The family had barely formed when the process of separation began. Today we can still witness such nurseries in the Orion Nebula, or the Carina complex glowing clouds, where gravity and chaos coexist, where stars are being born at this very moment. They are not static scenes, but living systems, breathing and unravelling simultaneously. One day those clusters too will vanish, their children scattered across the galaxy just as the Sun once was. It is humbling to realise that the process that forged our Sun continues ceaselessly. Every star we see is a descendant of such collisions, each carrying within its core the echo of the first collapse, the memory of motion, the logic of gravity, the rhythm of light emerging from cold. In this way, every night, skies both past and present, a frozen moment in an ongoing act of creation. And as we gaze upon it, we are in a sense looking into our own beginning. Because to understand where the Sun came from is to understand what made us possible, and to accept that we are the living consequence of a cloud that once dared to collapse under its own weight. In the stillness of a molecular cloud, gravity alone is not enough. For millions of years, vast curtains of gas can hang undisturbed, waiting balance between pressure and collapse. Something must disturb that balance, a spark, a shock, a tremor in the dark. Only then does creation begin. Astronomers call this the triggering mechanism, the event that transforms cold potential into motion and motion into light. Without it, a molecular cloud could drift silently through space for ages, carrying the promise of stars that never ignite. One possible trigger is the shock wave from a nearby supernova. When a massive star reaches the end of its life, it collapses under its own weight, then explodes with a force beyond imagination, a wave of gas plasma and radiation sweeping across the surrounding space. If that blast strikes a nearby molecular cloud, it compresses the gas just enough to tip it over the edge. Gravity takes hold and collapse begins. There is another possibility: stellar winds from young massive stars in neighbouring regions. These winds, travelling at hundreds of kilometres per second, can sculpt the cloud into arcs and bubbles, piling gas at the edges, until it collapses into dense knots. Even the passage of one molecular cloud through another, a slow, silent collision, can trigger a storm of formation. Everywhere in the galaxy, such events happen in rhythm like a heartbeat too vast for us to hear. When we trace the evidence backward, the story of our own Sun seems to fit this pattern. The isotopes embedded in meteorites aluminum-26 iron-60 hint that a nearby supernova occurred just before the solar system's birth. That explosion would have sent a wave of compression through the local molecular cloud, stirring regions of gas that had been quiet for eons. Within that disturbed space, the Sun's fragment began to collapse. Nearby, hundreds or thousands of others did the same. The Sun's family, the cluster we now call its siblings, was born not in calm but in aftermath. It's a poetic irony, a single death setting the stage for thousands of births. from destruction order arises, from chaos structure. The universe seems to favour this cycle, endings that are beginnings, boundaries that become bridges. Simulations of star-forming regions show how such processes unfold. A shockwave moves through a molecular cloud, folding and compressing it. Within those folds, dense pockets emerge, each destined to become a protostar. As the gas falls inward, it heats up and jets of matter burst from the poles, luminous outflows cutting through the darkness. In just a few 100,000 years, a blink in cosmic time, the region transforms from a shadowed void into a cluster blazing with newborn suns. If we could have stood there at the edge of the sun's birth cloud, we would have seen a scene both violent and sublime. A sky filled with glowing filaments, light spilling through torn veils of dust, and the constant hum of formation. Each new star would have its own disk of gas and dust spinning, shimmering the seeds of planets beginning to gather. Among them, quietly, almost unremarkably, our sun. But such nurseries are temporary. The same winds that trigger collapse also tear the region apart once the stars ignite. Radiation from massive blue stars strips the remaining gas, halting new formation. Within just a few million years, the once dense cradle becomes transparent, empty. The children have been born. The home has vanished. That is how most stars begin their journey in the ruins of something older. Even now, the galaxy is full of echoes of this process, bright arcs, pillars, and nebulae that mark the places where matter gave way to light. The Orion Nebula, the Eagle, the Carina, each a window into what the sun's birthplace might have looked like, moments before it faded into history. And if you listen to that thought long enough, it becomes clear nothing in the cosmos is ever truly isolated. Every spark owes its existence to a shock that came before. Every beginning is the continuation of something else's end. Our sun was no exception. It was a child of turbulence, a fragment awakened by the breath of a dying star. And in that paradox lies the essence of the universe itself, that even in collapse the cosmos is still creating. When the sun opened its eyes for the first time, it was not alone. Around it, thousands of newborn stars blazed with the same restless energy, a small constellation bound by youth and proximity. This was the solar birth cluster, the place that shaped everything that would follow. But even as it shone brightest, its unravelling had already begun. A stellar cluster is both a cradle and a storm. The same light that marks its beauty also marks its doom. As soon as the most massive stars ignite, they flood the space around them with fierce ultraviolet radiation. That light scours the gas and dust that once bound the cluster together, blowing it away like fog under the morning sun. Without that gas, gravity weakens. The invisible net that held the young stars in a shared orbit begins to tear. At first, the changes are slow, a few meters per second of relative drift, a subtle widening of distances. But time is relentless. 1 million years later, those small motions grow into vast separations. The cluster breathes outward, expanding like ripples in a pond. Each star, each sibling starts to follow its own path. For the sun, that path would become the story of our entire existence. Astronomers estimate that its cluster began somewhere closer to the galactic centre, perhaps 6,000 light-years from where we orbit today. Back then, the Milky Way's gravitational field was stronger, its tides sharper, its traffic of stars denser. Over billions of years, the sun and its siblings would slowly migrate outward, carried by the gravitational currents of the spiral arms. Their travellers, now scattered through the great disk of the galaxy, spread so thin that their common origin can only be traced through mathematics and light. This slow dispersal is guided by invisible hands. The galaxy itself exerts tidal forces, stretching and compressing, pulling stars away from their companions. Passing molecular clouds, dense and heavy, act like drifting giants, their gravity deflecting nearby stars. Every encounter adds a new note of randomness to the pattern, like dust disturbed by wind. And so the memory of the cluster fades its stars too far apart to feel each other's presence, their shared orbit, lost in the collective swirl of billions. It's a melancholy thought, a family separated not by conflict but by inevitability. Even if they could sense one another, their light would take hundreds of years to cross the growing gulf between them. They would shine together for a few brief cosmic moments, then vanish into the sea of the galaxy, each carrying within it the echo of the same birth cry. We know this pattern because we can still see it happening elsewhere. Look to the Pleiades, a glittering knot of blue-white stars young and close, or the Hyades, older, looser, already thinning at its edges. These clusters show us our own past in miniature. The Pleiades will disperse in another 100 million years. The Hyades are already halfway gone. The Sun's family, older by billions of years, has long since vanished from sight. Simulations of cluster evolution suggest that a group like the Sun's could dissolve completely in just 100 million years, less than 3% of the Sun's total lifetime. After that, its stars would wander free, indistinguishable from the background population of the galactic disk. Only their chemical composition locked within their atmospheres would preserve the record of their shared origin. And yet the Milky Way never forgets entirely. Every star that drifts across its arms leaves behind subtle gravitational traces, patterns in motion, resonance in velocity. By studying those motions, by rewinding their orbits through time, we can glimpse the moment when they were still one, a fleeting flash of unity in an ocean of dispersion. If we could have stood there 4.5 billion years ago, we would have seen the end coming even as life was just beginning. The cluster shining brilliantly in the cosmic dawn, its children beginning to wander. The sun turning slowly, already moving away, carrying with it a handful of dust and promise. A solitary traveller bound for a long, luminous journey, one that would someday give rise to oceans, to forests, to thought. Its siblings drifted into the dark, but the light they once shared still burns, woven into every sunrise on Earth. For decades, astronomers have searched the galaxy for clues for any trace of a surviving cluster that might still hold the Sun's long-lost family. One name more than any other once seemed to fit the description: 67. At first glance, it was almost too perfect. M67 is one of the oldest known open clusters in the Milky Way, rich with stars that share the Sun's mass, temperature and age. Its population contains more than 500 suns, a stable, well-preserved community orbiting in the outer disk of our galaxy. The resemblance was uncanny. Same type of stars, similar metallicity, the same chemical ratio of heavy elements that marks the Sun's composition. Even the age matched closely, roughly 4 billion years. Could M67 be the Sun's birthplace, the long-lost cradle where our star was born before wandering into solitude? The hypothesis captured imaginations. It offered something almost poetic, the idea that somewhere still intact, the Sun's brothers and sisters were shining together, orbiting in harmony, waiting to be found. But science is rarely satisfied with poetry alone. When astronomers began to test the theory with more precision, mapping orbits, modelling trajectories, the dream began to fracture. The first warning came from position. M67 lies about 2,700 light-years away, well above the galactic plane, while the Sun moves much closer to it. To reconcile the two, the Sun would have had to migrate upward by more than 1,000 light-years from its cluster, a journey difficult to explain through ordinary dynamics. Such a leap would require extraordinary gravitational encounters, perhaps with massive clouds or galactic tides, strong enough to hurl the Sun from its home. But the data showed no sign of such an event. Then came the motion problem. When astronomers rewound the orbits of both the Sun and M67 using galactic models, their paths never aligned. Not once in 4.6 billion years did their trajectories converge closely enough to share a common birthplace. Instead, the simulations revealed that M67's stars follow a distinct orbit, one tilted relative to the galactic disk, unlike the Sun's nearly circular path. In essence, the math ruled out the possibility. They were simply never in the same place at the same time. There were smaller inconsistencies too. The average chemical makeup of M67's stars while close to the Sun's isn't identical. Slight differences in elements like barium and yttrium suggest they were formed from slightly different clouds of gas. Close but not family, not kin. By the early 2010s, most of the scientific community had quietly let the theory go. M67, beautiful as it was, could not be the Sun's cradle. It was a sibling only in spirit, not in origin. Still, the idea had done its work. It proved that such a search was possible, that we could look across the galaxy and test hypotheses about our birth. It showed that memory can be reconstructed from motion and light, that even after billions of years the fingerprints of creation remain measurable, and perhaps most importantly it reminded us how fragile star clusters really are. Even one as old as M67, 4 billion years of survival, is an exception, a rare holdout in a galaxy where most open clusters dissolve within a few 100 million years. The Sun's own family would not have lasted nearly so long. It was likely gone before the Earth even finished forming. The failure of M67 was not an ending but a new beginning. It led astronomers to refine their search, to look not for entire clusters, but for individual stars that might still carry the Sun's chemical signature. The mission became more forensic, more intimate, not a quest to find a home, but to find one surviving relative hidden among the crowd. And so from that disappointment, the modern search began, guided by precision, spectroscopy, vast star catalogues, and the extraordinary eye of the Gaia Observatory. If the Sun's true siblings were still out there scattered across hundreds of light years, Gaia might be able to spot them not by brightness or proximity, but by the ancient code of their composition and motion. The journey would no longer be about finding a single cluster frozen in time. It would be about tracing a pattern of relationships across the galaxy, a family scattered so widely that its reunion exists only in data, not in light. The case of M67 closed one chapter, but it opened another. It taught us that the Sun's home is not a place but a story, one still being written in the quiet motion of the stars. And so as Chapter 2 ends, we leave behind the cradle of creation, the clouds of birth and the myths of origin, and turn our gaze outward toward the endless drift of stars, toward the silent shimmering ocean, where the Sun's sisters still wander, waiting for us to find them. To search for the Sun's true siblings, we must learn to read what the cosmos has left behind, the language of atoms, the stories written in light, and the silent records carried by stone. Every fragment of ancient material that reaches us from space, every meteorite, every cosmic grain embedded in ice, is a page from a book that began before the planets were born. These small dark stones are older than Earth itself. They preserve the memory of a time when the Sun was still wrapped in a cloud of gas and dust, when no planets yet existed, only the raw ingredients of everything to come. They carry traces of isotopes that no longer exist, of elements that reveal what kind of neighbourhood our star was born in. Inside these meteorites, scientists have found signatures of two radioactive isotopes, aluminum-26 and iron-60. Both decay rapidly on cosmic timescales, lasting only a few 100,000 years before transforming into more stable forms. Their presence in these rocks tells us something extraordinary, that the material which formed the solar system must have been enriched by a nearby explosion, a supernova that occurred just before the Sun came into being. It's as if our solar system carries a scar, a faint chemical reminder of the chaos that gave it life. Those isotopes could not have survived long in interstellar space. They had to be created and delivered almost immediately before the birth of the Sun. The timing, the proximity, the mechanism all point to a star that lived fast and died young, seeding the surrounding cloud with its final breath. And so our Sun's earliest environment was not a quiet nursery, but a crowded and dangerous place, one where new stars were forming beside the corpses of old ones. Each supernova blast was both destroyer and giver, compressing nearby gas while seeding it with heavy elements, carbon, oxygen, silicon, iron, the building blocks of planets, and much later of life. These chemical traces are not just history, they are coordinates. They help scientists reconstruct where the Sun might have been born within the Milky Way's grand structure. The pattern of isotopes, the ratios of metals, and the Sun's overall composition all suggest formation in a region rich in starbirth, near the dense inner arms of the galaxy, where such violent cycles of death and creation are most common. But chemistry alone cannot tell the whole story. For that, astronomers turn to light, the purest record of a star's identity. Every element leaves a distinct fingerprint in the spectrum of a star's glow, thin dark lines, precise and unchanging, carved across its light. These lines reveal what the star is made of, how hot it burns, and even how fast it moves. By comparing these spectral fingerprints, we can identify stars that share the same chemical DNA as the Sun. The idea is simple, yet powerful stars born from the same molecular cloud should have nearly identical compositions. Their light carries the same pattern of elemental lines, a family resemblance written in photons. This method, chemical tagging, has become one of the most promising tools in modern astrophysics. If two stars display the same spectral fingerprint and share similar motions through the galaxy, the odds increase that they are siblings separated by time but linked by origin. But there's a complication. The Milky Way is vast, and not all stars with similar compositions are true relatives. Many regions of the galaxy form stars from gas of nearly identical makeup, especially within the same epoch. Distinguishing coincidence from kinship requires precision beyond imagination, measuring differences of one atom in 10 billion, tracing orbital paths that span hundreds of millions of years. That is where missions like Gaia come in, the great cartographer of the galaxy. By tracking the motion, distance, and velocity of over 1 billion stars, Gaia allows scientists to rewind the clock of galactic motion to watch the Milky Way breathe backward in time. Through that lens, we can begin to see which stars may have once shared our sun's trajectory, faint echoes of a long-vanished cluster. It's not a simple story of recognition, but of probability, a search conducted not through the heart, but through the precision of data. Yet beneath that precision, something deeply human persists, the yearning to know where we come from, and whether the stars that lit our beginning still shine somewhere in the night, their light carrying the same forgotten signature of our birth. Light is memory. It carries within it every detail of what created it, the heat, the pressure, the chemistry, the history of a star. When that light reaches us, even after travelling for hundreds of years, it still holds the imprint of its origin. To the human eye, starlight seems uniform, white, steady, eternal. But when broken through a prism or a spectrograph, it reveals a secret language, dark lines, thousands of them carved into the rainbow. Each line is a syllable in the star's story, a fingerprint in the fabric of light. This is how astronomers decode the sun's identity. They study those lines, compare their spacing and depth, and translate them into elemental abundance. Hydrogen and helium dominate, of course, but sprinkled among them are trace elements: carbon, oxygen, iron, magnesium, nickel, silicon, the essential metals that define the sun's chemical DNA. Every star has its own variant of this code. No two are identical. But stars born from the same molecular cloud siblings in a cosmic sense share almost the same spectrum, differing only in the faintest of details. This is the foundation of chemical tagging, a technique that allows astronomers to search for the sun's lost family not by proximity but by pattern. Instead of looking for where the stars are now, we look for what they are made of, for the unique balance of elements that can only come from a shared origin. It is a kind of galactic genetics, mapping the heritage of stars through the signatures left in their light. To perform such analysis requires extraordinary precision. The lines in a spectrum are so fine that even the smallest instrumental error can mimic or erase a resemblance. That is why projects like Gaia, ESO, Apogee and Gala have dedicated years to collecting high-resolution spectra from millions of stars, building a vast library of stellar fingerprints. Each spectrum, when compared to the sun's, becomes a potential clue. Each match, a possibility. Among those possibilities, one star once stood out: HD 162826, located in the constellation Hercules about 110 light-years away. In 2014, astronomers announced it as a strong candidate for being one of the sun's true siblings. Its chemical composition was nearly identical, and its motion through the galaxy, though not identical, was close enough to suggest a common birthplace. It became a beacon of hope, proof that such searches could succeed, that the sun's family might yet be found. But science demands humility. Further measurements showed that while HD 162826 was close, it wasn't a perfect match. The uncertainties in motion and distance in the galaxy's gravitational model all introduce slippage into the conclusion. The star remains a candidate, not a confirmation. Still, it is a powerful reminder, even after billions of years, the traces of kinship may persist, waiting for us to notice. Finding those traces is not easy. Every star is in motion, and the galaxy itself is a living system, a rotating spiral of 400 billion suns, each tugging on the others, each slightly altering the paths of its neighbours. Over time, these motions blend together like ripples in an endless sea. The longer we wait, the harder it becomes to separate memory from coincidence. But that is precisely what makes the search meaningful. If we could gather enough of these stellar fingerprints, enough stars with the same spectral genome as the sun, we could reconstruct the long-lost cluster. Not as it is now, but as it once was. A digital resurrection of our star's birthplace. A simulation of the cradle where the sun first ignited, surrounded by hundreds of others, all shining together in the same cosmic dawn. That is the dream behind Gaia's mission, to map not only positions, but ancestry. To reveal the structure of the Milky Way not as a flat diagram, but as a family tree branching, overlapping, alive. Every data point a name, every trajectory a memory. It's strange, isn't it, that in the age of advanced telescopes and quantum optics, the question that drives us remains ancient. Where do we come from? We look into light to find our beginnings. We break it apart to hear the echoes of our birth. And perhaps somewhere within that faint pattern of spectral lines, among the thousands of tiny marks that define the sun's light, lies the connection we have been searching for, a single shared signature linking us back to the cluster that time has erased. Even if we never find it, the search itself matters, because every act of observation is an act of remembering. Every spectrum we read, every element we trace brings us closer to understanding that the sun and everything it gave rise to is part of something larger, a pattern, a lineage, a whisper of unity scattered across the galaxy. The siblings may be gone, their light may have drifted too far to ever converge again. But the code they share, the spectral genome that once bound them, endures in the light that touches our world each dawn, and in that light, if we listen closely, the family still speaks. If we could rewind the motion of the stars billions of years in reverse, perhaps we would see a sight now lost to time, a single glowing cluster drifting through the arms of the Milky Way, carrying within it thousands of newborn suns. Some blue and massive, destined to burn out within mere millions of years. Others smaller, cooler, fainter, still alive today, scattered like embers across the galaxy. Among them was one that would one day warm oceans and awaken life, our sun. But that once brilliant family is now gone. All that remains is a faint pattern, too delicate for the naked eye to see, written in the positions and velocities of stars that no longer remember each other. A family fractured not by catastrophe, but by time. The process began almost immediately after their birth, as the most massive members of the cluster ignited their powerful stellar winds, and radiation pushed away the remaining gas, the glue that once held the stars together. With that binding force gone, gravity weakened. One by one, the siblings began to drift apart, first slowly, then faster drawn into the complex tidal fields of the galaxy. Astronomers simulate this process using computer models, letting thousands of virtual stars orbit the galactic center under the influence of gravity alone. In every simulation, the result is the same: the cluster unravels. After 100 million years, it has stretched into a loose stream. After 500 million, it is gone entirely, its members indistinguishable from the background stars. And yet, even in that dispersal, faint structures remain. Groups of stars with similar velocities, moving groups as they're called, drift through the galactic disk like ghosts of ancient clusters. Our sun may once have been part of such a group. Some models suggest that for a short time after the cluster dissolved, a few dozen of its siblings may have continued travelling together, bound not by gravity but by shared momentum. They would have appeared as a subtle streak of light across the Milky Way, their paths aligned, their origins forgotten. But over billions of years, even that trace was erased, the gravitational tides of spiral arms and molecular clouds scattering them in all directions. This scattering was not gentle. As the sun and its siblings moved through the galaxy, they passed close to other stars' gas clouds and the dense concentrations of matter that ripple through the Milky Way's disk. Each encounter altered their trajectories slightly, a tug here, a nudge there, until the cluster's collective motion disintegrated completely. Some were drawn inward toward the galactic center, where the gravitational forces are strongest. Others were carried outward toward the quieter edges of the spiral arms. A few may have been flung into higher orbits above or below the plane of the galaxy, like sparks rising from a fire. The sun's own path took it outward, away from the chaos of its birthplace. Today we orbit in a relatively calm neighborhood, a safe distance from the violent star-forming regions near the galactic core. Perhaps that migration was the key to life's emergence on Earth. Had the sun remained where it was born, among the radiation storms and supernova blasts of younger clusters, the delicate balance that allowed our planet to flourish might never have survived. And yet there is a quiet sorrow in that safety. To find life, the sun had to leave its family behind. Its journey towards stability was also a journey towards solitude. Still, the evidence of that family lingers. When astronomers study the chemical composition of nearby stars, they find a few, very few, that match the sun's spectrum almost perfectly. Each one is a possibility, a faint reminder that not all connections are lost. Perhaps one or two of the sun's siblings orbit quietly not far from us, their light blending into the starfields of the night sky unnoticed. If we could identify even one with certainty, a star that was born from the same cloud as the sun, we would be looking not just across space but across time itself. It would be a reunion measured in light years and eons, a proof that memory, however fragile, can outlast dispersion. The sun's family is gone, yes, scattered beyond recognition. But in the galaxy's great architecture, nothing ever truly disappears. Every star still carries the rhythm of its origin, the momentum of its beginning. And so even now, though separated by the breadth of the Milky Way, the sisters of the sun continue their long silent dance, each following a path shaped by the same first spark that once bound them together. For decades, astronomers have been searching through the immense sea of stars, guided by one simple but haunting question: are any of the Sun's siblings still out there? The Milky Way holds more than 400 billion stars, and among them perhaps a few dozen might share the same origin as our own. Finding them, however, is like trying to recognize a single drop of water from a river that has been flowing for billions of years. The search begins not with the eyes, but with light. Every star carries within its glow a code, its chemical fingerprint. The idea is simple: if two stars were born from the same molecular cloud, they should have nearly identical chemical compositions. The ratios of iron, magnesium, silicon, carbon all trace back to the environment that forged them. These ratios form what scientists call chemical abundance patterns, a kind of stellar DNA that can reveal familial relationships across space and time. With the help of vast surveys like Gala, Gaia, ESO and Apogee, astronomers now compare millions of spectra in search of these fingerprints. Each spectrum is a possibility, a potential voice from the Sun's forgotten family. But the task is immense. Two stars can share almost identical compositions. By coincidence, the galaxy is large, and its chemistry repeats itself in patterns. To find a true sibling, one must go beyond chemistry. That's where motion comes in. The Milky Way is not still, it swirls, flexes and ripples under the pull of its own gravity. Every star moves in a precise orbit, and those orbits can be traced backward like footprints through deep cosmic dust. If two stars' motions converge when rewound billions of years into the past, the odds grow that they were once close, perhaps even born together. This is where the Gaia mission becomes indispensable, a spacecraft mapping more than 1 billion stars with unprecedented accuracy, measuring their distances, speeds and directions. By combining Gaia's motion data with chemical tagging, astronomers began to narrow their focus. Among the billions of lights in the sky, a few began to stand out. The first and most promising was HD 1622826, discovered in 2014. Located about 110 light-years away in the constellation Hercules, this star is nearly identical to the Sun in mass, temperature and metallicity. Its motion through the galaxy also appeared loosely compatible with a shared origin. For a moment, the astronomical community allowed itself a breath of wonder. Could this be it? Could we be staring at one of the Sun's long-lost sisters still burning quietly across the void? But as always, the closer the data, the more complex the truth becomes. HD 1622826 is similar but not identical. Later simulations using refined galactic models showed that its trajectory only nearly intersected with the Sun's presumed birthplace. The resemblance, while striking, wasn't perfect enough for certainty. Science as ever demands restraint where mystery invites emotion. Other candidates soon followed: HIP 437, HD 1630, and a handful of unnamed stars detected by chemical clustering algorithms. Each held a hint of familiarity, a whisper of shared ancestry. But one by one, most fell away under scrutiny. Their ages, their compositions, or their orbits revealed subtle mismatches: too much iron here, too little magnesium there, or a trajectory that diverged by millions of years. Each time the excitement dimmed, replaced by a patient, almost meditative persistence. Yet this persistence is what defines the search. Every false lead refines the path forward, narrowing the criteria, sharpening the instruments. We are in a sense learning to listen better, to detect the faint echoes of the Sun's childhood in the endless background noise of the galaxy. Still, one must ask, what would it mean if we did find them? If somewhere within a few hundred light-years a star truly born alongside our Sun were discovered, would it change how we see the sky? Would we look at that point of light and imagine it watching us back, remembering the same dawn of creation? Perhaps the meaning is more symbolic than scientific. Finding the Sun's siblings would not just solve a cosmic puzzle, it would connect us to a deeper truth that even in a universe of dispersion and decay, kinship endures. The atoms that compose our bodies, our oceans and our air, all came from that same primordial cloud. In a way, every one of us is already a continuation of that ancient family. Still, the search continues. Gaia's data grows richer with each passing year, its catalogue expanding, its precision sharpening. Somewhere in that database may already lie the coordinates of a true sibling star unnoticed, for now waiting for someone to see the pattern that unites it with us. The challenge is not just technical, it's temporal. After 4.6 billion years of motion, the Sun's family has drifted so far apart that only mathematics can remember the bond. But mathematics, like memory, is patient. And perhaps one night through the hum of data and the shimmer of starlight, the connection will reappear, a faint thread stretching across the galaxy, a confirmation that even after eons of silence, the family of the Sun was never truly lost. Not every clue to the Sun's lost family shines like a star. Some move through the darkness more quietly, small, cold, and ancient. They are not suns but fragments, remnants that may have drifted across the void from the same nursery that once cradled our solar system. If stars can disperse across the galaxy, then so too can the debris that formed around them. Asteroids, comets, and icy planetesimals, each carrying the chemical memory of their birthplace, can travel astonishing distances when gravitationally disturbed. Over billions of years, the boundaries between stellar systems blur. Matter trades hands. The universe, it seems, is not a static archive, but a slow, endless exchange. That idea has led to one of the most intriguing branches of this entire investigation, the non-stellar hypothesis, the possibility that traces of the Sun's lost siblings might not be stars at all, but interstellar objects now wandering through or even trapped within our solar system. Consider the case of C2018 V1, a faint and short-lived comet discovered just a few years ago. Its trajectory was unusual, not quite fitting the long-stretched paths of ordinary comets, nor the expected curve of an interstellar visitor like 1I Oumuamua. Some astronomers speculated that C2018 V1 could have originated in a stellar system, born alongside our own, a frozen messenger dislodged from the debris disk of one of the Sun's ancient sisters. If that were true, it would mean that even now, billions of years after the family scattered the remnants of that cluster, still brush against one another, their fragments crossing paths by pure cosmic chance. And then there is Sedna, a world so distant and detached from the planets that it seems almost orphaned. Its orbit stretches from 76 AU at its closest approach to nearly 1000 AU at its farthest, far beyond the realm of Neptune, yet still bound to the Sun by a thread of gravity. How did it end up there? Its elongated path defies the standard models of solar system formation. One leading theory suggests that Sedna's orbit was shaped by a close encounter, perhaps when the Sun still dwelled within its birth cluster. A passing sibling star could have tugged gently on the edges of our primordial disk, scattering icy bodies outward and capturing a few of its own in return. If so, Sedna may be a survivor from that time, a fossil of the Sun's earliest neighbourhood, a piece of shared history preserved in orbit. This exchange of material between stars is not rare. Modern simulations show that in dense stellar nurseries, close encounters can easily transfer comets and planetesimals from one system to another. Some may become interstellar travellers, drifting freely for billions of years until caught by the gravity of a new host. Others remain loosely bound to multiple suns, following long elliptical paths that trace invisible bridges between families long dispersed. The Sun's siblings then may not all be distant points of light. Some could be within reach fragments of their disks mixed into our own, indistinguishable from native matter. It's a haunting thought that somewhere among the countless comets that sweep through our skies, one might be an immigrant from another sun that was born beside ours, a grain of dust forged in the same collapsing cloud travelling through time to return home. The implications reach beyond astronomy. If material can travel between sibling systems, then so too can the basic ingredients of life. Microbial spores, organic molecules, or amino acids encased in icy shells could have crossed the void this way, carried from one forming world to another during the cluster's brief chaotic youth. This is the foundation of the panspermia hypothesis, that life, or at least its precursors, might have spread between stars like pollen in a cosmic wind. If that is true, then our origins are not only shared with the stars, but perhaps with the life that might exist around them. A biological kinship woven into the same stellar heritage. The Sun's siblings would not only be our cosmic relatives, but possibly our genetic ones, a vast interstellar family of worlds linked by exchange, by coincidence, and by the stubborn persistence of life. Of course, it remains speculation, a beautiful, dangerous kind of wondering. No comet yet studied carries the irrefutable mark of an alien system, and no proof connects Sedna's odd path to a sibling star, but the possibility endures, whispering that not all memory fades into the dark. Perhaps the proof is already here, circling silently beyond Neptune, waiting to be recognized, a relic of another sun, a frozen handshake between the past and the present, between what we were and what we came from. Although calculations suggest that the Sun was likely born in a stellar cluster containing thousands of stars, most of which may still exist today, we must face the reality that no true sibling of the Sun has yet been reliably confirmed. This failure likely arises from the strict limitations of the three fundamental criteria we rely on to trace stellar origins. We must therefore question in depth the accuracy of each one. First, the imperfection of stellar age determination. The basic assumption is that stars from the Sun's birth cluster should have approximately the same age, about 4.6 billion years. Yet this is precisely where uncertainty begins to creep in. We know the Sun's age with high precision because we have direct access to the oldest samples in the solar system meteorites asteroids and can apply radiometric dating. For distant stars, however, we must rely on complex stellar evolution models that estimate age based on luminosity, colour and metallicity. This raises a crucial question: could even small discrepancies in these models distort our results, causing us to overlook a genuine solar sibling simply because of uncertainties in age estimation? Second, the uniqueness of chemical composition. Using spectroscopy, often described as a DNA test for stars, the assumption is that stars born from the same molecular cloud share nearly identical chemical signatures, yet this criterion remains deeply uncertain. Are molecular clouds across the galaxy chemically distinct enough to allow us to clearly separate stars born from the Sun's parent cloud from those formed elsewhere? Complicating matters further, there have been observed cases in which stars from entirely different clusters share nearly identical chemical compositions, implying that such matches could occur by coincidence. Moreover, the quality of stellar spectra is itself a major obstacle. Low-resolution spectra from distant stars make it difficult to compare enough elemental abundances to reach a firm conclusion. Third, the uncertainty of galactic dynamics. The assumption here is that a sibling star's orbit should trace back to the same birth region as the Sun. However, reconstructing an orbit over 4.5 billion years, roughly 20 galactic revolutions, is an extraordinarily complex task. While Gaia has provided highly precise measurements of present-day positions and velocities, dynamical models can only yield probable trajectories, not absolute ones. This raises a key question: could a candidate that best matches the Sun's kinematic profile merely be a statistical coincidence in our simulations rather than a true sibling? In summary, the limitations and uncertainties within each of these criteria have led early optimistic estimates, suggesting dozens of solar siblings within 100 parsecs to be reconsidered as overly hopeful. When more sophisticated models that account for galactic dispersion are applied, those numbers drop sharply. Thus, the core issue is not whether these stars exist, but whether current methods and technologies are capable of eliminating all doubt and providing conclusive 100% proof of their shared origin with the Sun. If we acknowledge that the shortcomings in confirming current candidates primarily stem from limitations in measurement precision and modelling accuracy, then the scientific premise is that the key to identifying the Sun's true stellar siblings lies in a comprehensive upgrade of our instruments, and analytical methods for these tools are still evolving. Specifically, to eliminate ambiguity in the criterion of chemical composition, we need more powerful telescopes capable of capturing spectra with greater detail. The underlying hypothesis is that the more elemental abundances we can compare, the lower the probability of random coincidence becomes, thereby offering more convincing evidence of a shared origin. At the same time, to overcome the fact that current dynamical models only provide probabilistic trajectories, we must construct more intricate and higher resolution simulations capable of reconstructing stellar orbits over the Sun's 4.5 billion year journey through the galaxy. Furthermore, as new generation telescopes are launched, they are expected to deliver higher quality spectral data, allowing for improved calibration of stellar age estimates. An especially intriguing prospect is that in the near future, we may be able to capture a sample of an interstellar object such as Oumuamua or 3ALC. By backtracking its trajectory, scientists could determine its parent star and thereby infer its exact age. In summary, the overarching assumption is that advancements in observational technology, the advent of next-generation telescopes and the development of more sophisticated models will together pave the way for identifying a truly undeniable solar sibling, one whose kinship to the Sun can be confirmed beyond any reasonable doubt. After analysing the inherent limitations of current methods and outlining the hypothesis of a future technological revolution, we must return to the central question: why does finding these stars matter so much? The strongest scientific premise is that confirming a true sibling of the Sun would open the door to reconstructing the entire evolutionary history of the stellar cluster in which the Sun was born. It would also allow us to verify or refute existing theories such as the hypothesis that the Sun may have formed closer to the galactic centre and later migrated outward. However, the greatest significance lies in the search for life. We must ask, could the emergence of life on Earth have been the result of unique formative conditions, such as the optimal chemical composition of the original molecular cloud, or a cluster density low enough that nearby stars did not destabilize the orbits of forming planets? If we accept the assumption that these conditions were crucial, then the Sun's sibling stars, those born in the same cosmic cradle, might have a higher probability of hosting life-bearing planets than random stars elsewhere in the galaxy. Moreover, the concept of panspermia, the idea that life or its building blocks can be transferred from one stellar system to another, suggests that if life once took root on Earth, the same mechanism could have seeded life on the planets of the Sun's siblings as well. Therefore, although no solar sibling has yet been reliably confirmed, it is clear that observational methods and technologies are rapidly advancing. We have good reason to believe that a candidate sharing a common origin with the Sun may be discovered in the near future. If that happens, scientists will be able to focus their search for life, including potential biosignatures and technosignatures, on these systems, greatly narrowing the scope of the search for life within our galaxy. Having proposed that advancements in technology and modelling will inevitably lead to the discovery of a star that shares a common origin with the Sun, one whose kinship can be confirmed beyond any reasonable doubt, we must now ask the next critical question. Will this search end merely with an astronomical identification, or could it open a new era in the search for life? The scientific premise is that such a discovery would immediately allow us to focus our research efforts on the confirmed stellar system. The first step would be to reconstruct the evolutionary history of the Sun's birth cluster, thereby revealing precisely where and under what conditions the Sun was formed. This could confirm or challenge existing hypotheses, for example the idea that the Sun may have originated closer to the galactic centre before gradually migrating outward. Yet the greatest significance lies in the hypothesis concerning the origins of life. If we accept that life on Earth may have arisen from a unique set of formation conditions such as the optimal chemical composition of the primordial molecular cloud, or a cluster density low enough to prevent neighbouring stars from destabilising nascent planetary orbits, then the Sun's sibling stars would have a significantly higher probability of hosting life-bearing planets than random stars elsewhere in the galaxy. Therefore, the search for planets around these solar siblings would become a top priority. If such planets are found, we could immediately conduct in-depth investigations for biosignatures, signs of biological activity, or even technosignatures indicators of advanced civilizations. The hypothesis of panspermia further supports this effort. If life, or the essential building blocks of life such as complex organic molecules, could have been transported to Earth from space, then the same mechanism might also have seeded life on the planets orbiting the Sun's siblings. If this were ever confirmed, the discovery of a solar sibling would not only mark a monumental achievement in astronomy, but would also provide a powerful and efficient strategy for narrowing the search for life in our galaxy by concentrating on systems that share both a common origin and unique formative conditions with our own solar system. Although we can conclude that the Sun almost certainly formed alongside thousands of siblings in a dispersed stellar cluster, the greatest uncertainty lies in where they are now. The failure to trace them primarily arises from the immense complexity of galactic dynamics over 4.5 billion years. The scientific assumption is that neither the Sun nor its birth cluster has remained in their original positions. Instead, they likely formed closer to the galactic centre and have since migrated outward by about 1.9 kiloparsecs, or roughly 6,200 light-years. Over this long journey, during which the Sun has completed more than 20 orbits around the galactic centre, each lasting over 200 million years, the original sibling stars have become widely dispersed, possibly even residing on the opposite side of the Milky Way today. This presents an enormous challenge since current dynamical models can only produce probabilistic trajectories, not absolute orbits over such vast timescales. The complexity grows even greater when we consider that the Sun and its stellar relatives have continually passed through and out of spiral arms regions shaped by density waves, not fixed structures. The hypothesis is that within these spiral arms, where both stellar and interstellar matter densities are higher, the Sun's siblings would have experienced significant gravitational perturbations, encounters with molecular clouds and enhanced stellar interactions, all of which could have subtly yet unpredictably altered their orbits. In summary, this search is not merely a matter of distance, but a profoundly complex problem of galactic dynamics, where the combined effects of large-scale migration and the continual influence of density waves have scattered the Sun's long-lost siblings into nearly chaotic orbits throughout the galaxy. Uncertainty increases significantly when the three core criteria, age, chemical composition and dynamics, come into conflict, causing even the most promising candidates to be dismissed due to a lack of consistency. This leads to the conclusion that despite meeting one or two criteria, the best candidates are ultimately rejected because the three do not align perfectly. The case of HIP 40317 clearly illustrates this paradox. The star matches the Sun remarkably well in both age and chemical composition, which are the two most intrinsic indicators of common origin. Yet its dynamical trajectory contradicts the hypothesis of kinship with the Sun. Similarly, HD 1630 was once considered one of the most promising candidates in a study, but later refined dynamical modelling rendered it far less plausible. This raises a critical question. Even when a star's age and chemical signature perfectly align with the Sun's, can we ever claim 100% certainty if its reconstructed orbit does not trace back to the same region of space? In reality, we can find stars that are nearly identical to the Sun, in both age and composition, so-called solar twins, but these similarities do not imply a shared origin. Hence the final conclusion is that although the hypothesis of the Sun's siblings remains scientifically strong, identifying a true solar sibling requires a perfect alignment among all three fundamental criteria, a condition that to this day has never yet been achieved. We can conclude that the search for the Sun's siblings is not limited to distant stars because evidence of a shared origin may in fact lie within our own solar system, in the form of small bodies that were left behind or captured during the dispersal of the Sun's birth cluster. An intriguing hypothesis proposes that some distant objects in the solar system may have been captured by the Sun during a close encounter with one of its sibling stars when it still resided within a dense stellar nursery. A prime example is Sedna and other trans-Neptunian objects with elongated and highly inclined orbits. It is hypothesized that these trajectories may provide indirect clues about the sibling star involved in such a capture event, since the star responsible for this gravitational disturbance or capture must have been a member of the Sun's original birth cluster. Beyond captured objects, we can also consider interstellar bodies that have entered the solar system. It has been hypothesized that some of these may have originated from the Sun's siblings. For instance, Comet C 2018 V1 was once proposed as a possible interstellar object that might have come from a solar sibling, though its true interstellar nature remains debated. However, the key scientific assumption is that if in the future we're able to capture and analyze the chemical composition of a confirmed interstellar object, and if its elemental fingerprint matches the unique chemical signature inferred for the Sun's birth cluster, this would constitute direct and irrefutable chemical evidence of a solar sibling bypassing the nearly impossible task of reconstructing 4.5 billion years of stellar orbital history. Thus, we may conclude that a careful study of these small and enigmatic bodies within our own cosmic backyard could represent the shortest path to uncovering direct evidence of the common origin of the solar system, although we can state with confidence that the Sun almost certainly formed within a stellar group, with early estimates suggesting that its birth cluster may have contained several thousand or even up to 20,000 stars, and the scientific assumption that 1,000 or more of its siblings may still exist today, it is crucial to emphasize the distinction between solar siblings and solar twins. Solar siblings are stars that share a common origin with the Sun, having formed from the same molecular cloud. Solar twins, on the other hand, are stars that merely resemble the Sun in mass, temperature, chemical composition, and age, but do not share any genealogical connection. A solar twin could have formed on the opposite side of the galaxy and simply happens to look like the Sun by coincidence. The greatest discrepancy between theory and observation lies in the fact that while early simulations suggested that several dozen solar siblings might be located within 100 parsecs, about 326 light-years of us, such estimates are now considered overly optimistic. When scientists conducted more advanced simulations taking into account a wider range of galactic effects capable of dispersing stars, the predicted number of nearby solar siblings dropped sharply. As a result, despite strong theoretical support for their existence, not a single solar sibling has been confirmed with 100% reliability to date. If we step back from the details from the chemistry of isotopes, the fading trails of clusters, and the faint whispers of comets, a broader picture begins to emerge. It is the story of continuity, not isolation. The Sun's lost family is not just a historical curiosity. It is a reminder that nothing in the cosmos exists alone. Every star, every fragment of dust, every molecule of carbon in our breath, all are part of a single circulation that began long before the Earth existed. The elements that now compose our oceans were once trapped inside ancient stars long gone. The atoms in our blood were born in collisions between galaxies in the brief radiant deaths of giants. When the Sun was young, the Milky Way was more turbulent. Clusters formed and died like waves, each one seeding the next with new material. In those early epochs, stars exchanged matter, influence and motion more easily than they do now. Some of the Sun's siblings may have inherited material from still older clusters, and in turn our solar system may have passed fragments of itself to others. Over time, this cycle blurred the boundaries between ours and theirs, between one system and the next. Across billions of years, these exchanges turned the galaxy into a living continuum, a single interconnected ecosystem of light and gravity. Every sunrise, then, is not just the light of our star. It is a mixture of photons from countless ancestors, blended through the vast chemistry of time. Perhaps this is the truest meaning of the search for the Sun's siblings. It is not merely about finding a handful of stars that once shared a birthplace. It is about recognizing that we are all fragments of the same unfolding process, that every star is kin to another, and that somewhere in the quiet rhythm of the galaxy, memory itself is what binds us, flowing between worlds, between stars, never lost, only transformed. There is a kind of music in the way stars move, not in sound, but in rhythm. Each orbit, each slow arc across the Milky Way is a note in a vast composition written over billions of years. The Sun once played its part in harmony with thousands of others before drifting away into its long solo. But the melody continues faintly through the gravity that still links it to those unseen companions. When we look at the night sky, we see stars as points fixed, unmoving. In truth, they are travelers crossing unimaginable distances in silence. Every one of them carries within its motion the story of its birth, the imprint of the cluster that once surrounded it. Even when time scatters them beyond recognition, the memory of that shared momentum remains embedded in their paths. The Sun's orbit too is not static. Over billions of years it has drifted outward, oscillating gently above and below the galactic plane like a heartbeat. These slow waves caused by the uneven mass of the galaxy are reminders that even the most stable light we know is still in motion, still part of something larger. And perhaps somewhere along those gentle oscillations, the Sun's path still crosses the faint traces of its sisters, invisible threads of shared history stretched thin but unbroken. It is tempting to think of the galaxy as a machine, orderly, mechanical, predictable. But it is closer to a living organism, pulsing, breathing, exchanging energy between its parts. Gravity is its heartbeat, light is its blood, and stars, like cells, are born live and disperse, yet remain connected through the invisible circulations of matter and memory. So when we speak of the Sun's siblings, we are really speaking of continuity, of how creation never ends, of how even separation cannot erase the symmetry of a shared beginning. The universe does not forget. It only changes the form of its remembrance and waits for us patiently to learn how to see it. Light is the one messenger that never truly dies. It leaves its origin and travels onward unceasing, carrying with it the history of what once was, even after the source itself has changed beyond recognition. When we look up and see the stars, we're not witnessing the present. We're looking into the preserved memory of the galaxy. Every photon is a letter from the past, crossing millions of years to reach our eyes. The Sun's siblings may have faded into distance, their orbits scattered across spiral arms, but their light still threads through the interstellar medium. Even when absorbed by dust, re-emitted or scattered, the energy of their existence remains part of the Milky Way's quiet glow, a diffuse remembrance that fills the space between stars. In this way, the galaxy itself becomes an archive not of names or positions, but of radiance, a record of every star that ever was. Perhaps this is why astronomers chase light so tirelessly. It is not just to measure or classify it, it's to listen. Every wavelength carries the tone of an event, the trace of a reaction, the whisper of a process that connects one world to another. In studying that light, we are tracing the migration of meaning across the universe. The Sun, too, contributes to that ongoing exchange. Its photons spill into space, cross the orbits of the outer planets, and continue outward into the interstellar dark, where one day they may fall upon another star's world. In that distant system, perhaps orbiting one of the Sun's forgotten sisters, the faintest gleam of our daylight might touch alien dust and scatter once more, joining the endless tide of starlight that binds the galaxy together. No matter how far the stars drift, their light remains intertwined an invisible web that unites all suns, all worlds, and all time. It is the language of remembrance that the cosmos speaks to itself, and as long as that light endures, the sun will never be alone. Every act of creation leaves an echo, not a sound, but a resonance that moves through space and time. Stars are born in silence, yet their births ripple outward, altering everything around them. The explosion of one massive star seeds the next generation. The gravity of one cluster stirs the clouds that will one day give rise to others. It is a cycle that began long before the sun, and one that will continue long after its final light fades. The search for the sun's siblings is in truth a search for that resonance, an attempt to hear the lingering vibration of a single event that took place nearly 5 billion years ago. Some traces are obvious, the isotopic clues locked inside meteorites, the faint signatures written in stellar spectra. Others are less direct, woven into the very dynamics of the galaxy, the way certain stars still move in faint synchrony, the way their compositions hum with the same underlying pattern. Each fragment is a note in a song that has never truly stopped playing. Across the vastness of the Milky Way, these echoes overlap, merge and fade into one another. The boundary between what is the sun's origin and what is simply galactic inheritance becomes impossible to draw. But perhaps that ambiguity is itself the message that creation is not a single moment but a continuum, that the sun's birth was not an isolated spark but one pulse within a living resonant field of formation, stretching across the arms of the galaxy. And within that resonance lies something quietly profound. We too are part of that same vibration. The carbon that shapes our cells, the iron in our blood, the calcium in our bones, all carry the atomic rhythm of that long ago cluster. Every heartbeat is a faint echo of stellar fusion, a microscopic reflection of cosmic creation. So when we listen to the universe, to its silence, its rhythm, its balance, we are not listening from outside, we are hearing it from within. We are the continuation of its echo, the living memory of the moment when light first learned how to last. From the first spark of its birth cloud to the quiet solitude, it drifts through today. The story of the sun is not one of isolation, but of connection. Every discovery, every hypothesis we've traced from the clustered origins, the chemical fingerprints, the scattered siblings, to the silent visitors that may still carry fragments of our shared past, all point toward the same truth that the cosmos remembers. The sun was never a solitary creation. It was part of a greater ensemble, a stellar symphony, formed in the dense heart of a molecular cloud, where gravity, chaos, and radiation wove together the first bonds of family. Those bonds were not broken by distance, only stretched by time. Each star that shared that cradle continues to move in rhythm, their orbits threading unseen patterns through the Milky Way echoes of a common beginning still vibrating beneath the surface of the galaxy's calm. In the search for those lost siblings, we have learned more than we expected. We found that memory in the universe takes many forms: the decay of ancient isotopes preserved in meteorites, the spectral lines written across starlight, the improbable paths of distant worlds like Sedna, and the faint gravitational resonances that ripple through the galactic disk. Each is a fragment of a story far larger than the sun itself, a cosmic genealogy that stretches beyond stars, beyond systems, into the very chemistry of existence. Perhaps the greatest realization is that we are part of that story too. The matter that builds our bones was once suspended in that same cloud. Our planet's oceans shimmer with the oxygen that once burned in the hearts of those long-lost suns. Even the photons that warm our skin today carry the same atomic rhythm that once flowed through the cluster of our star's birth. We began with a question: where are the sun's sisters? And we end with a deeper one: what does it mean to be connected in a universe built from dispersal? The answer quietly is this: nothing in the cosmos ever truly leaves its origin. Every orbit, every particle, every breath of light is part of a single ongoing conversation, a dialogue between matter and memory. And somewhere drifting through the spiral arms of the galaxy, that conversation continues still. If we were to look at the Milky Way from afar, not as astronomers but as witnesses, we might see it not as a structure of arms and stars but as a single living geometry of memory. Every thread of gas, every orbiting sun, every grain of drifting dust forms part of a pattern too vast for any one lifetime to perceive, and yet within that immensity there is coherence and order that speaks softly through motion and light. The sun, like all stars, is a point within that geometry. But its journey tells us something profound about existence itself, that movement is not separation, but continuation. Its slow migration through the galaxy, away from its birthplace, through clouds of dust across gravitational tides, is not exile, but evolution. The distance that divides it from its siblings is not loss, but transformation. Through dispersion, the universe renews its own structure, redistributing the memory of creation so that no place remains untouched by its origin. And in that sense, the sun's path and our own becomes an act of belonging. We belong not to one cluster, one star, or one epoch, but to the continuum that links them all, to the rhythm of cycles that repeat endlessly, birth, expansion, dispersal, and rebirth. Even when we imagine the sun travelling alone, it moves within a gravitational ocean, where every motion is influenced by countless others unseen but present. Its solitude is only apparent. Connection, though invisible, remains constant. This understanding changes how we see everything. The stars are not scattered, they are synchronized. Their separations are only the pauses between harmonies. Their migrations are the galaxy breathing. And within that breath, we tiny and transient become part of the same structure that once gave birth to light. Perhaps then the purpose of seeking the sun's lost family was never to find specific names or coordinates, but to rediscover what it means to be of the universe, not merely in it. To recognize that across every scale from atoms to galaxies, the same quiet truth endures, that creation is a circle, not a line, and that everything born of light sooner or later returns to it. In the silence of deep time, the universe forgets nothing. It only learns to speak in quieter ways, through gravity, through light, through the endless motion of stars carrying their stories across the spiral arms. The sun, our constant companion, was once just one among thousands, a single spark in a dense nebula of dust and gas. For a brief moment it shared its infancy with other stars of every colour, every mass, every future. Some blazed and vanished in brilliance, some wandered outward dim and patient, others may still burn today, their light crossing the night sky unseen. The family is gone, but the pattern remains a whisper carved into the fabric of the Milky Way, still pulsing with the rhythm of its beginning. To trace that rhythm, we followed every sign the cosmos offered us. We read it in the language of isotopes, in the fractures of meteorites older than the Earth. We heard it in the hum of galactic motion, the way stars drift like echoes through the gravitational tide. We found it in the spectral DNA of light itself, in the fine black lines that tell us what a star remembers of its birth. And even in the dark, we sensed it through comets, through Sedna's lonely orbit, through the fragile bridges that link one system's dust to another's. The further we searched, the more it became clear the sun's siblings were not merely other stars. They were states of connection, manifestations of a single truth written in different forms. The same atomic ratios that define the sun shape the chemistry of our oceans. The same cosmic shockwave that once triggered its birth gave rise to the elements of our breath. And the same light that warms our mornings has travelled far enough to touch the dust of other worlds, perhaps orbiting one of the sun's forgotten sisters. We began this journey asking a scientific question. We end it with a human one. What does it mean to belong to a universe that never stays still? Perhaps it means that belonging is not a matter of proximity but of resonance. We belong to everything whose rhythm we share, to the hydrogen that fuels our sun, to the iron forged in another star, to the unseen hand of gravity that keeps us within the Milky Way's slow embrace. Even across billions of years and billions of miles, we remain connected not by memory, but by motion, by light, by the unbroken continuity of existence itself. Look up then, not for recognition, but for reflection. Every star that shines is a possibility not just of life, but of kinship. Each one a reminder that we are the galaxy, remembering itself molecule by molecule, orbit by orbit. We are the dust that learned to dream, and in doing so rediscovered the pattern of its own creation. The sun will continue its long voyage for billions of years more. It will rise and set, breathe light into the earth, and one day release that light back to the stars. When it finally fades, it will not vanish. Its atoms will scatter, carried by the winds of time to seed new worlds, new beginnings. Somewhere in a far future, we will never see a new star may form from that dust, and in the flicker of its light, the memory of our sun will live again. This is the circle that holds us. from the first fusion in a collapsing cloud to the heartbeat of life, on a small blue world, everything is part of one continuous act of becoming. The stars are not distant fires, but mirrors. They do not shine to be admired. They shine to remind us of what we are made of and of how long creation has been whispering our names. So when you look into the night sky, let the silence between those lights speak to you. Imagine the unseen web of motion connecting them all, the slow dance of siblings long separated yet never entirely apart. Know that somewhere, perhaps hundreds of light years away, another star burns with the same ancestral rhythm as the sun, its light still carrying the echo of that shared beginning. And in that understanding, may you feel the quiet comfort that the universe offers, that no journey, no distance, no dispersal is ever truly unending. Everything returns to its source in energy and form in memory. Even light in the end finds its way home. For when the cosmos breathes again, when another cluster forms and another sun is born, that breath, that spark, that fusion of elements will still carry the same pattern we have traced here. The pattern of belonging, the pattern of continuity, the pattern of the universe remembering itself,